Get started with the recording. So welcome to my class on materials, and a big portion of which is about nanocrystals and quantum confinement and some applications, but is largely about how to think about bonding in solids and how to study their structure and their electronic structure. So it's, inorganic materials kind of 101, and it's a attempt to teach you some solid state physics, but we're not really going to be driven by mathematics like you would get in a traditional solid state physics course. That being said, I think if you're interested in this topic, it's really a good idea to take solid state physics at some point. A lot of the people in my group in the past have done that successfully and have gotten a lot out of it. So hopefully this will inspire some of that. An interest in that for you. Okay, so I'm going to begin by sharing my screen here. There we are. So this is the website for the class, and I've intended to get a more recognizable domain name going and haven't quite gotten it up to speed yet. It won't be too long now. Can you give me a thumbs up if you can see the screen, please? Yeah. Okay. Thank you. Yeah. I mean, one more thing about Zoom, it really is nice for me to be able to see people's faces. And so, because I think these experiences are kind of lonely, not only lecturing, but being a student in the class. So I would appreciate it if you guys would turn on your cameras and participate. If I ask a question or whatever, speak up. It's nice to get a little bit of interpersonal communication through the screen. Okay, so here is a website for the class, and it basically provides a list of how we're going to do grading, and then a description of the manuscript reviews, which we'll talk about here in just a moment. Note here, the first one is due at the end of January on Mondays, and they're going to be weekly. And so every Monday, you're going to have to turn in one of these written reviews. Class participation is something that ends up determining whether you go up or go down. It's worth 5 percentage points, which is actually kind of a lot. You look at the way the grades spread, and a 0 in class participation category is definitely a B+ instead of an A- or whatever. We're going to do a final exam. March 7th is the midterm date. That's our last lecture. So there will be an exam scheduled on that date, and it's going to be a traditional closed note exam. We'll see whether we're in person at that point, and we'll figure out exactly how that's going to be done. If it's, a take-home exam, you'll probably get 24 hours to turn it in or something to that effect. So there are a couple of different textbooks that I especially like, one of which is The Electronic Structure and Chemistry of Solids. That's by this guy, P.A. Cox. He's got a bunch of different books. This one is very user-friendly, and quite a bit of the material that you're going to see here is taken from that text. Okay, so it's a very inexpensive and small book. Must have left it at home, but readily accessible and a great way to learn this stuff. So we're going to start by going through a lot of the text there and talk about, work our way up to talking about energy versus momentum diagrams, which are a physicist's way of talking about molecular orbital structure in solids. And we're going to talk about things like excitons and carriers and excited carriers and semiconductors, and how those things lead to charge separation or luminescence. We're also going to talk about crystal growth, because synthesis is a big part of the game here, and it's the thing that I know the most about. So we'll talk about models of crystal growth, which are sort of mind-bending and sometimes counterintuitive. And then we'll talk about applications of nanocrystals toward the end of the class. Um, I am intending to add some material on oxides and perovskites in this course, although I have not put that material together yet. So we'll see how that goes. I will post lecture recordings here. I taught this spring class in the spring of 20 during the shutdown. So there are recordings. The link to those lectures is there. And I probably will replace them with recordings of this year's lectures, but I've left them up for now. Weekly manuscript reviews are going to be a big part of this class. And, you know, sorry, I'm noticing a typo here. The first one is due on Monday of January 31st. These assignments, you know, in the past, the students in this class have said that this is their favorite part about the course. I don't know what that says about my lectures, but I think it's a pretty useful exercise, okay? And when I was an undergraduate, I had to write a weekly paper for a philosophy class that I was in. And it really taught me about reading and writing in a way that I, you know, really hadn't experienced before. It reminded me a bit about having to learn derivations for thermodynamics. You know, you really go through the motions when you have to spit it all out. And writing is a big part of the game in chemistry. So you need to have lots of practice with writing. So I have, over the years, kind of refined the formula for how this is done. And the point here is for you guys to go out and read the literature on inorganic materials, and then to take those papers and to referee them. Okay, you're supposed to write a critical assessment of the manuscript according to the format shown below here, or shown on the website. So we'll walk through the format in just a second here. But the object is to teach you guys to read critically, you know, not just to kind of regurgitate what's there, but to actually evaluate whether or not the work is of good quality, whether you believe it, whether it's an important contribution, and to make a statement about why. Okay, so I want you to have, I want you to make an argument about the work, not just tell me what it is. Is it good? Is it thoughtful? You know, whatever. I want a real value judgment. Okay. So I want you to use this format. Look at it very carefully. You should use 1-inch margins and 12-point font, Times New Roman single space. Okay. And don't make bulleted lists. I want you to write paragraphs. I want a real narrative description. Okay. I want to see all of these details about the paper. You know, just copying the sort of like title and author list and where they're from, etc., is a good idea. It's helpful for me to see the abstract. I often have to go and look up the paper myself, which is fine. If you want to provide a link, that's helpful. But I want to see all the information about the manuscript on the cover so I can easily identify the paper. And then page 2 of this thing, I want you to fill a page with text. Okay, that's it. Just one page. Do not go over a page if you possibly can. Learning to say something in few words is maybe more important than writing more. So try not to go over one page, but I want you to fill a page. Okay, so can't be a couple of sentences. I want you to break these things out in the following way. I want to hear about the significance of the work. All right. Whenever you submit an article to the Proceedings of the National Academy of Sciences, they ask for a significance statement to be included with the manuscript. Okay. And the point here is to talk about the work on a very basic level and to really capture the value in it and communicate it to anybody. You know, so if you have an undergraduate science major friend, they should be able to read this thing and understand what it means. And your ability to make a very clear and compelling statement about what it is that's there and why it matters is the goal here. And then what's the take-home message of the work? Okay, so like really what was learned? What are the significant observations or demonstrations that support the take-home message? What's the sort of like brass tacks accomplishment here, which is different than its significance, right? I want you to sort of summarize the really the key thing, and then how they've came to that. So what's the data that supports their claim? And then finally, and notice this is the majority of what I want here, the critical assessment is about 2/3 or more than half. I want you to critically evaluate. What does that mean, critically evaluate? And what I'm trying to say is I want you to dismantle the paper or defend it, okay? And I want a value statement. Is this good, right? It should not just be an analytical thing. It should be a evaluation of the quality, okay? And in particular, their argumentation. People make statements about what they've done, and sometimes it's really not rigorous. Let's see here. Sorry, I had to add somebody. Okay, and then if you want to add any figures or anything like that to help support the discussion, that's fine. Add them as the third page. Okay. All right. So when I look these things over, I'm going to give you a grade. If you're late, you're going to lose 5 points. If you're 2 days late, you lose 10 points. Okay. And after 2 days late, there's not going to be any kind of a grade. You're going to get a 0 for the homework set or for that review. So I'm going to look at the relevance and importance of the manuscript. If you give me a paper about something that has very little to do with the topic of the class, in my mind, that's low relevance. What is it we're trying to discuss and learn about here? Okay, and let's pick things that are relevant to what the course is about. It's going to be hard to do that by January or by January 31 if you don't know, the topic yet, but I think you kind of will get the point there. And then, if it's not an important paper, if it's sort of like a boring thing that's, not really exciting or not earth-shattering, well, I'm not going to give you a high score. So I want you to pick things that are meaningful. And then the quality of the presentation and writing is a big piece of this. If the thing is full of typos or it's not formatted according to the rules, you're gonna get marked off for that. And then depth of analysis and critical insight is the main thing that I'm concerned about. So half of the grade is how insightful is the statement that you're trying to make, and am I getting something out of this or not? So this is somewhat different than what you would do if you were to referee an article that gets submitted for publication, but the idea is to help you kind of think like a referee a little bit. Okay, so you can, when you do, if you have not already, when you do submit papers for publication, you can maybe begin to think a little bit about how a referee might look at your own work, hopefully as a result of doing this. Okay, I've listed a bunch of reading assignments down here. I need to update the dates on these, I see. In addition to Cox, I want you to take a look at this Feynman article and then a bunch of these other articles as we go along. A very important one is How Chemistry and Physics Meet in the Solid State, which is something that Roald Hoffman wrote. It's a book. It's also been published as an Angewandte article. And so I've provided a link to it here, and the particular sections of that article that we're going to talk about. This is a really nice presentation of molecular orbital structure of solids, and I think it's really worth the time to go and read it. Hoffman is a master of teaching these sorts of ideas to people. He's a really, really eloquent person and terrific speaker. And this particular thing is something that chemists, solid state chemists all over know about this text, and it's really a classic in the chemistry of solids. So I strongly encourage you to go read it. A lot of the material that we're going to talk about is taken directly from it. And then we'll transition to talking about quantum dots. the optical characterization of them, et cetera, et cetera, et cetera, and so on. I think I'll go check also that these are all still functional. Regarding the reviews, I've provided a list of potential journals that you might turn to. This is a pretty good list. There's a few that I might add. But if you're not sure where to go looking for a paper, these are all good options. One last thing about that point, in addition to just encouraging you to read the literature, I would say more broadly, it's a very good idea to begin, if you're not already, you should begin paying attention to the table of contents of journals and keeping your eyes on what's getting published. There's a variety of ways to do that. People use feeds, RSS type services to curate a list from all their favorite journals. They keep track of particular authors, that type of thing. It's really a good idea to get in the habit of scanning those table of contents every day. And keeping track of what's coming out, and then skimming papers, looking at the abstract, looking at the conclusions, going through all the figures, or reading the whole thing if you're really serious about that material. It's a challenging, a daunting thing because there's a tremendous amount of work getting published, but you need to identify the things that matter to you, and you need to pay attention to what matters to the community. And so learning to do that is also a part of the reasoning behind this literature review assignment. Okay, so I'm going to update this with the correct dates to sort of give you a sense of when we're going to be doing what, and get this posted on the courseworks page so that you can find it. Okay, I'll be sure to make it available to you after the class today. All right, does anybody have any questions, or you want me to expand a little bit on the manuscript reviews? Nothing? Oh, I did also provide examples here. Yeah, this is, I've forgotten who wrote this one. Yeah, there's a couple of them. I think these were written by an undergraduate. Yeah. Okay, so you can go flip through those, and that'll give you a sense of kind of what I'm looking for. I'm going to do my best to give you feedback, especially on the first one or two, but it's challenging for me to keep up with reading and grading all of them. So we'll see how that goes. If you're uncertain about a paper, also, if you go out looking for a paper and you sort of say, well, this is relevant to my research, but I'm not really sure it's relevant to class, just send it off to me and I can kind of give you a sense of my own impression. And I don't want to be draconian about what you read and write about. It does impact your grade, but it's important that you're focused on the things that matter to you also. So, there's plenty of overlap there, I think, hopefully. Okay. Shrink this down. All right. Everybody sees that, I imagine. Thank you. So a lot of this class is about colloidal nanocrystals. And, the properties of these materials are really fun and interesting. And they are the chemist's version of solids that were first prepared in vacuum chambers. Okay. Well, there's some truth to that. So a lot of the very interesting behaviors that are seen here in these kinds of materials were studied in depth by physicists in solid state devices. And so there's quite a bit of overlap there between those topics. The thing that really stands out to me when I look at these pictures is the incredible precision with which these materials can be prepared. So on the left, you can see these really wonderfully faceted crystals I believe these are palladium. They may also be silver. I've forgotten now. But you can make solids that are basically like molecules in the sense that every single crystal in the sample is alike. On the right, you're looking at, and the left is metals. On the right, there are oxides and semiconductors being shown there. And in fact, an interesting thing about these is that there are actually two different crystals that have co-crystallized into a supercrystal. This is kind of like the cluster assembled materials being studied by Colin and Xavier's groups. But they don't have any sort of covalent attachment. They're just they're coated with organic ligands that makes them fluid, and they form these kinds of lattices simply because of the monodispersity of the crystals. The size dispersion of each of these samples is so small that they pack like ping pong balls in a box. And you get all kinds of different superstructures that are very interesting to think about as a consequence of the very narrow size distributions. So, the real goals of this class as related to nanocrystals are to understand that electronic structure and to understand how solids form. What is it that makes it possible to prepare a sample of this kind? The last thing that I wanted to point out here is that, these things really do have almost discrete molecular formulas, and you can study them with all kinds of fancy new techniques, and in particular, things like X-ray scattering, electron scattering, and electron microscopy. Those tools have made this field possible. The image down there in the lower left is actually pretty old now. That is taken from a 2008 article. And in that time period, it was pretty straightforward to go in and get atomic resolution images of the materials involved. And electron scattering and those methods have really only improved since that time and are providing incredible amounts of detail. So that's a big reason why this whole field is possible. So we'll talk about that also. Okay, so Richard Feynman is somebody that gets credit for having kind of anticipated the study of or the development of this field. And it was back in about 1960, he gave this talk about miniaturization, this idea that we're making things very small. And he talks about writing the Lord's Prayer on the head of a pin. Okay, and so, or how about the Encyclopedia Britannica? Does anybody know what an encyclopedia is? They don't, I don't know. When I was a kid, I had volumes, like 24 volumes, each one with a different letter on the front of it. And, you could go pull off the letter T and flip through and find an article about tomatoes or whatever. And so that's how information was curated. Back in 1960, the idea that you could put, the entire contents of your life on a cell phone was a totally foreign concept. And, Feynman kind of anticipated that it would become increasingly important. All right, so take a look. There's this article I posted on the page. Go read through it and sort of think back to, what people were imagining at the time. So what has happened since then? Quite a bit. One of the things was the discovery of this device here. And in 1947, this thing was made. And in 1956, these three fellows, the Bardeen, Britton, and Shockley, were awarded the Nobel Prize for this device. Maybe some of you have heard me speak about it before, but this is the world's first transistor. Okay, it's probably not the first one, but it's the most presentable of the first ones. And in fact, the key element in this transistor is this block of germanium down here, this silvery crystal that's sandwiched between this electrode and that electrode. That semiconductor made this transistor possible. Okay, people like Lou Bruce and Mike Steigerwald used to work at Bell Labs, where this device was first pioneered, and they were inspired by the developments that followed. And in fact, it turns out that Bell was a company that made the telephone industry possible. And it used to be that when you called somebody, there was somebody at a switchboard that would move a cable around and connect you to the line that you were trying to call. And they quickly realized that this was not very scalable if they were going to make their company, something that served the entire population of the US. So there was a basic science effort that went into creating better switches and led to this device. All right, so quite a bit has happened since then. Those devices led to computers like this one here. This is a computer from 1960 that was at IBM. And this is what's called a punch card computer because of these cards right down here. These cards are, I don't know, if you voted before, there's a little booth where you go, you punch out a little hole in a piece of paper that indicates, who you want to vote for. And then they take those cards and they feed them into machines that go and look for which holes got punched out. And so that's how computers were first fed information. They had hard drives composed of magnetic tape, like you see on the wheels back here. And then back behind this panel is a bunch of transistors that were made, sort of miniaturized versions of what you saw in the previous slide. I imagine that most people's smartwatches are far more powerful than this computer, which was, 1960. I was born in 1978. Okay, so this computer is not that old because I'm not that old, despite the gray hair. I am not that old. So imagine a world without any of this stuff. People were imagining what it might be like if everybody had such computers, including the Rand Corporation, who proposed this idea as part of their consulting work, to think about how we could take advantage of home computers. And they went about sort of projecting what it might look like in 2004. Probably everybody here was born before 2004, but they were a long way off from being right. My favorite part about this is the steering wheel that this guy is standing in front of. But, I think it's very helpful to just try and wrap your head around what has happened. 1960, not that long ago, 50 years or 70 years has evolved since then, and it's a totally different world. So what has happened? Well, the biggest thing is miniaturization of transistors, okay? Transistors have shrunk, and the reason is that what people have learned to do is they take a big ingot of silicon and they slice it into wafers, and they take these wafers and they've learned to pattern transistors on the wafers, and the feature sizes that can be drawn on those wafers have gotten smaller and smaller and smaller. And so there's this thing called Moore's Law that was coined by Gordon Moore. He was a Caltech undergraduate and started IBM, I believe, or Intel, I've forgotten. And he basically made the statement that the number of transistors that you're going to put into a computer chip or on a die, as it's labeled here, was going to double every 2 years. Okay, so you're going to have this sort of exponential growth. You can see a log scale here going from 10 up to 10 billion transistors over this period of 1960 to 2010. So that exponential growth in the density of these transistors, which are switches, led to much, much more powerful computers. And I graduated high school in 1996. Okay, so I think we got our first computer in like 1993. And things were very slow. It was exciting to have the internet at home. You go to a website and an image would load line by line. It would appear on the screen, scrolling in, and you used your telephone to call in to an internet service. In any case, computers have gotten, people always wanted to get a new computer during that period because the computer chips got more and more powerful. But this has basically stopped. Computers, I'm about to buy another computer. The last two computers that I owned were essentially the same in terms of their potency. I'm not expecting big improvements out of the next one. And it's because there's no more room. They can't actually write transistors any smaller. That was not always the case. So what's happened is that the transistor sizes, the features of those devices now are really reaching molecular length scale. So to give you a sense here, the feature sizes that are patterned back in 1960 from that punch card computer, you're talking about 10 to 100 microns in dimension. Those are circuit elements that are like on the length scale of your hair, or a very, very thick hair anyway. And over the subsequent 50 years or so, people learned to pattern things down on the length scale of molecules. So buckyball is about a nanometer. Buckyball is C60. It's about a nanometer in size. The COVID virus is about 100 nanometers in size. So amazing what people have learned to do with lithography. But there's a limit. You basically can't go much below 100 nanometers. That's the reason the computers have not gotten more powerful. The reason, people are talking about making molecular computers, I don't think that's very realistic, but there is an interest in that sort of thing. So what happens when you get down to that length scale? All kinds of really interesting things happen. And, it's the main driving force behind a huge collection of fields in science. In biology, for example, people are also interested in that same length scale. The sort of 1 to 100 nanometer length scale is a rich area of research. Things like machines in your body that make your muscles move, or the ribosome, for example, translating DNA, is a little machine that's a few nanometers in size. I don't know exactly how big the ribosome is, but I bet it's on the order of 10 to 20 nanometers or something. And the function of those macromolecules is something that people are actively very interested in, like the Gonzalez group, for example, and a wide variety of other biophysicists who are tackling the very unusual behavior of those types of materials, and just developing techniques to learn how to study them. The same issues occurring here in, like, this image got screwed up, but the same sorts of length scales are very interesting in the solid state and organic world. Physicists have learned to miniaturize things, and they can make transistors out of molecular length scale stuff like nanotubes. They can also pick atoms up and move them around. This image now is 20 years old, roughly. A bunch of iron atoms that were moved around with a tunneling microscope tip and made into what they call a quantum coral, and then the electronic structure imaged with that tip. So physicists have gotten really good at manipulating stuff on that length scale, and chemists have gotten very good at making things on that length scale from the bottom up, and that's kind of the perspective we're going to take. But the point is here that across biology and physics and chemistry, a big chunk of it is really devoted to the nano world, as it's labeled here. All right. So, when you get to that size scale, the thing that really changes is that the number of surface atoms goes up compared to the amount of stuff that's in the middle. Okay. So I've plotted here the number of atoms in the bulk of a material versus the number of atoms on the surface. And that basically inverts. So, if you have a really big crystal, there's not a lot of surface area compared to the amount of stuff that's in the middle. As you shrink that down below about 10 nanometers in particular, that can switch, where the amount of surface exceeds the amount in the middle. And this has all kinds of consequences. Okay, for electrical conductivity reasons, that you might be interested in a transistor, there are huge effects of having very little bulk and a high amount of surface. So some important things to remember, of course, is that area goes as r squared and volume goes as r cubed. And so the surface area to volume ratio is basically 1 over r. And, it leads to all kinds of fun stuff like melting temperature changing. Okay, and it's really because surfaces tend to be more reactive and tend to be more weakly bonded than the material in the middle of the crystal. And that leads to melting temperature changes of 1 over r. So, a big crystal melts at a higher temperature than a little crystal does. A small droplet of water evaporates more readily than a large droplet does. And it's because of that increase in the amount of surface compared to the bulk. All right. A very important principle that we're going to talk about is something called quantum confinement. Quantum confinement is a property where the electronic structure is limited by the size of the material. And so people talk about the box in which the electron lives. So you're very familiar with particle in a box theory, where the wave function for the electron is truncated at the walls of a potential well with sort of infinite depth. It leads to these discrete wave functions. I like to think about these as standing waves. If you have an example where somebody is taking a rope in front of your physics class or chemistry class and vibrating it as fast as they can, you get two fixed points on the rope. And then these waves develop, and the harder you vibrate the string, the higher the frequency of the wave. And there are only discrete waves that form these sort of standing wave patterns that are stable, okay? And then the width of that space, of course, determines the energy of the electron, according to these equations shown up here. Okay, so the energy level spacing in these standing waves is related to the size. It goes as 1 over r squared. The number of electronic states that you have in a given region of energy goes as the volume of the material. There are also things like charging. If you have a crystal that you're putting an electron into, you have to pay a coulombic potential that is related to the radius, okay, and goes as 1 over r. So all kinds of very interesting properties in these materials, thermodynamic, quantum mechanical. Ooh, I have frozen. Everybody has frozen. There we go. Both thermochemical and quantum mechanical properties are size dependent on this length scale because of this surface area to volume effect. All right. So quite a bit of the materials that we're going to discuss relate to these sort of semiconductor heterostructures. So in the upper left, I've shown an example of a colloidal quantum dot. The quantum dot is one of these quantum confined structures. They are the sort of classical ones are made out of cadmium and selenium, or cadmium and sulfur, or zinc and sulfur and selenium. And it turns out that you can get all kinds of really interesting properties when you combine these materials. Okay, and as I said, the synthesis of these things was sort of taken or inspired by work that had been done in solid state devices like the one that you see on the lower left. So that little column, which is color coded in purple and blue, is what's called a multiple quantum well. Okay, and each of those different colors is actually a different formula. So gallium is yellow, indium is purple, aluminum is blue, and there's this sort of like birthday cake stack of these different crystallites. You can see here in the electron microscopy image, there's contrast differences visible. And look at this scale bar. It's 20 nanometers is the scale bar here. So you're talking about just a few nanometers thick. These crystals have been grown on top of each other with essentially perfect connectivity. This device that you're looking at here is actually a light emitting diode. So, the LED that you have in your home, if you have LED lighting, is composed of structures of this kind. The growth of one crystal on top of another one leads to all kinds of effects. And there's been a huge amount of work, especially in the 2,6 and 3,5 semiconductor classes. 2,6 refers to the valence of, or the number of valence electrons that are used by the element. So zinc and cadmium have 2 valence electrons. Sulfur, selenium, and tellurium have 6 valence electrons. And when you make a combination of those two, you get to 8. And so binary semiconductors like cadmium selenide are binary because there's only 2 elements. And they have an 8 valence electron count. They're sort of like the simplest, closed shell types of solids out there. Same is true for gallium and phosphorus, or indium and phosphorus. Those guys also are 3,5. Gallium has 3 valence electrons. Phosphorus has 5. You also get 8 when you make a 1-to-1 semiconductor out of those materials. Those are semiconductors that have been studied in great detail because they're powerful light emitters and powerful light absorbers, wonderful for making photovoltaics, transistors, and the like. Quantum dots and solid state light bulbs go together. So, the latest and greatest televisions now are being made from these kinds of materials, not just the colloidal quantum dots, but also the epitaxial quantum wells. Here's an example of an LED. That multiple quantum well is actually this little yellow strip that you see here. It's got gallium in it. And it's wired up in this example with a gold contact and an aluminum contact. You drive an electrical current across this staircase of 3-5 quantum wells, and this crystal produces blue light with almost perfect efficiency. This thing is 1/4 of a millimeter by 1/4 of a millimeter across, and a few microns thick. It's a tiny, tiny little flake. And it takes a huge amount of current and converts it to light very efficiently because of that stack. Those kinds of devices go into the latest and greatest displays. Quantum dots actually absorb the light produced by those crystals and re-emit it as the colors of the display, particularly the red and the green. We'll talk about that in a little more depth later. But these are incredibly important materials to society, penetrating consuming huge amounts of power, for example. They're really a big deal. So we'll talk about some of that. Another set of materials that's really important are metals. Nanoparticulate metals have gone into all kinds of different technologies. A classic example is the Lycurgus cup. This is a cup that was made with gold or silver. I don't know exactly which one is in it, but it has this really unusual property that if you look through it, it's red. And if you look at the light scattering off of it, it's green. This is a consequence of the optical properties of tiny pieces of gold and silver. We'll talk about that in a little bit more depth. Another more modern example of metal nanoparticles and their optical properties anyway are gold nanoparticles. They're very, very strong absorbers and scatterers of light. And so if you have a home pregnancy test, or I imagine also a COVID rapid test, the pigment that's used in these things are little gold nanoparticles because their absorptive and scattering properties are so very, very strong that it takes very little for you to see, essentially. So they're very sensitive as a result. Okay, so there's all kinds of applications of colloidal materials, and we'll talk about a variety of them as the class goes on. All right, so as I said, one of the main things that interest me in this area is what controls the size of these things. It's possible to make materials that have really narrow size distributions because of the thermodynamics and the kinetics of their formation. And this is something that is still not very well understood. And it's surprising considering how easily people seem to be able to make these kinds of things. But it's really not been adequately explained why this happens. And there are sort of two types of explanations. One is a kinetic explanation, and the other is a thermodynamic one. Thermodynamics can lead to clusters. I differentiate nanocrystals in clusters based on the uniformity of their structure. So here's a couple of examples of so-called magic size clusters. The clusters studied in Xavier and Collins groups also are of the same sort of type, where you get only one formula present. It really is molecular in its uniformity, and this is a consequence of thermodynamic effects and some kinetic effects as well. But it's primarily a thermodynamic consequence where you have a particularly stable geometry. The same types of thing can lead to flat crystals like these colloidal nanoplatelets, as they're called. They're kind of like the quantum wells that I showed you on the previous slide. They're very large in the lateral dimensions, but they have molecular perfection in the thickness direction. Also a consequence of thermodynamics. So we're going to spend time exploring exactly how that happens and getting into that thermochemistry. All right, so there's a huge amount of research that we're probably not going to talk about, but we will to some degree. People sort of realize this connection between the optical properties of the thermochemical properties and the fact that it was possible to synthesize materials that had such narrow size distributions. And there was kind of a bonanza of papers going out making different substances. It used to be that you'd open the Journal of the American Chemical Society, look at the table of contents, and every single day there would be a new paper about a new crystal that had been synthesized that had a different shape and it was a different substance, and was branched or hollow. For example, hollow is a big one. Of course, things like metals were being made and wonderful, like unusual semiconductors that physicists love. So there was there was a lot of effort poured into how one synthesized and what can be synthesized using colloidal techniques. Another really big thing that's been happening at the same time is, as I mentioned, electron and X-ray scattering. We're going to spend some time talking about how powerful synchrotrons are and the variety of techniques that are accessible there. This is an example of a conglomerate. It's a bunch of different crystallites that are all sandwiched together, and using a focused X-ray beam, this group, I think might be from Simon Billinge's lab, I'm not sure. They came in with a focused beam and could actually map every single one of these crystallites. And in addition to these kinds of things, there's the more traditional scanning probe methods out there, and then electron microscopy. So electron microscopy, people are doing experiments now where you can actually watch atoms move around in the microscope in real time. So we'll talk about exactly how that works. Okay, so enough introduction here. We're going to sort of jump into some of the electronic structure. Just take a look at the time. So we're going to start talking about molecular orbitals. I think almost everybody here has had my inorganic class. But remember, when you take two wave functions, two atomic orbital functions, and combine them, you end up with two molecular orbital functions that are linear combinations of those atomic orbitals. And this leads to bonding and anti-bonding combinations. And this linear combination of orbitals approach to molecular orbital theory is really sort of intuitive and powerful. And as I said, Roald Hoffmann's article is all about this kind of thing. Remember that as you go up in energy, you tend to get more nodes, okay? And we're going to talk about the energy of interaction being equal to this, this value beta that's labeled here as we go forward. Another very important point that we're going to look at is what happens when you have two different orbitals of different starting energy. So in the case of sodium chloride, the ionization energy of this atomic orbital is offset because sodium is more easily ionized than chlorine is, or chlorine is more electronegative, so its energy starts lower than sodium's does. And when you combine these two, you again get bonding and anti-bonding combinations. But now we're combining a 3p orbital and a 3s orbital. Those are the valence orbitals of those two elements, and they lead to bonding and anti-bonding orbitals. And an important property that we've talked about in my inorganic course is that the wave function of the product bonding and anti-bonding level look like the atomic level that they're sort of closest to. So this bonding level looks a lot like a chlorine 3p orbital, and that means that the coefficient in front of that atomic orbital in this linear combination is larger. Okay, and the depiction of the orbital reflects that sort of thing. Okay, so yeah, all right. So now, what happens if you take this sort of principle and you look at it in the solid state? Okay, we're used to thinking about a few atomic orbitals interacting. You get bonding and anti-bonding levels, and in a molecule you get many molecular orbitals. But in a crystal, you get so many of these sort of linear combinations that you end up with what physicists refer to as bands of orbitals. Okay, and we're familiar with the idea of HOMO and LUMO gap. In the solid state, you have something that's called a band gap. okay, referring to these bands of orbitals, but it's essentially like the HOMO-LUMO gap. An important property of these sorts of things that we're going to talk about is something called the density of electronic states, which is the number of allowed energy levels, or the number of molecular orbitals per unit volume of the solid. It's got volume units because you've got to define by how much if you're counting the number of levels in a particular range of energy. Okay. And that's plotted here on the x-axis. Okay, so it's not just a collection of orbital energies, but it's also a reflection of how many orbitals there are in a given range of energy. If this were actually labeled with numbers, we would have to, as I mentioned, define the volume over which we're integrating. The presence of this band gap, last thing here, is a very important property of the solid. It's what makes something a semiconductor or an insulator. And that presence of that gap and the magnitude of it is something we're going to pay a lot of attention to. In a luminescent material, it defines the color. It defines the conductivity of solids in many cases. You know, a semiconductor classically defined is really a solid that's a moderate conductor of electricity, okay, as opposed to a metal, which is a good conductor. But specifically, the classic definition is that the conductivity increases with temperature, right? That's a consequence of this band gap here. This property of the conductivity is also sensitive to the presence of impurities, as we'll see, but that's the sort of old school way of talking about things. If you have different semiconductors, like here I've shown here sodium chloride, zinc sulfide, and zinc telluride to illustrate the band gaps here. So we have the conduction band and the valence band as are labeled by physicists. And remember that these orbitals here, they're really sort of very much like the, sorry, I want to be able to back up. There we go. You know, we're taking combinations of these orbitals and getting molecular orbitals that in the case of sodium chloride are sort of defined by the starting energy of the sodium and the chlorine levels. Okay, so when we go forward and take many sodium and chlorines and make molecular orbitals out of them, the product valence band is a lot like the starting chlorine level. Okay, it's close to the starting chlorine level in energy. The product conduction band is a lot like a combination of sodium 3s functions. Okay, the molecular orbitals that you would write, the coefficients would be largest on the sodiums. And so people tend to talk about the conduction band as being primarily determined by the sodium level. It's, you know, it's defined by the sodiums as opposed to the chlorines. It's not that simple, but that's sort of a good rule of thumb. And the band gap energy is kind of related to the starting difference between the sodium and chlorine levels. And we'll go into more detail about what really defines it. But you know, that molecular orbital picture really does translate very well for a wide variety of materials. When you move towards zinc and sulfur, now you're actually changing the extent to which the two starting states are separated. So zinc and sulfur, you know, the top level is primarily zinc, because zinc is more electropositive than sulfur and starts at a higher energy than sulfur does. And the valence band, the bottom of this diagram, is defined by the sulfurs, sulfur P3 or 3p orbital combinations and zinc 4s. Now, it's a linear combination of both elements, but you know, it is zinc 4s like, okay? And the band gap that you get, again, is related to the difference in energy between the zinc and the sulfur. Comparing zinc telluride and zinc sulfide, what you end up with is a conduction band that's actually very similar for both materials, because the conduction band is primarily zinc 4s in character. But you get a big difference in the valence band. Okay, the valence band goes up relative to the sulfur level because the tellurium 5p level is more easily ionized than the sulfur 3p level is. Okay, so the valence band energy on this vacuum scale can be related to the ionization energy of the element or of the anion. The result for zinc telluride is that the band gap shrinks. Okay, so the zinc level is sort of consistent in both cases. The tellurium goes up. This leads to a much smaller band gap. And now you're in a region 2.23 EV. We're definitely in the visible. 3.5 EV is in the ultraviolet. 9 electron volts is an X-ray. Okay, so this band gap energy dictates the color of these semiconductors. This one is white. It's not used as a sunscreen, but it could be. Zinc telluride, definitely not used as a sunscreen. Probably it's a brown material that absorbs all the way across the visible. All right, so a distinction between an insulator and a semiconductor is sort of arbitrary, but it's essentially something that has a band gap of greater than 4 electron volts. Anything, zinc sulfide is arguably an insulator. It is, I would say, considered a semiconductor or described as a semiconductor, but that's about as wide of a band gap as you're allowed. Anything higher than that, is an insulator. It's not going to be a very good conductor at all, at least in its intrinsic state. All right, anybody want to ask anything about this? No? Okay. All right, so I've provided here a table showing all the different sorts of semiconductors that are out there, labeled by group. So group 4 is diamond, silicon, and germanium. 3,5 nitrides here, indium nitride, gallium nitride, aluminum nitride. The phosphides and antinomides of 3,5 semiconductor materials. We've got 2,6 materials and then a bunch of oxides down here, titanates, tantalates. And you can look at this table and think about the ionization energy and electron affinities of all of these different substances. So let's take a look at the zinc sulfide, selenide, and telluride series. Notice up here, this is the bottom of the conduction band. This is the top of the valence band. And above this level, you have, above this energy, you have many energy levels that are empty. And below this energy, you have many energy levels that are filled. Notice here, the 3 of these, zinc sulfide, zinc selenide, and zinc telluride, they share approximately the same conduction band energy. Clearly, there are differences between the 3 semiconductors, but they're about the same. Look down at the valence band, you can see the sulfide, selenide, and telluride going up. Same is true for cadmium sulfide, cadmium selenide, and cadmium telluride. The valence band levels climb. The conduction band levels are pretty consistent. Zinc and cadmium have a big difference. Zinc is more easily ionized than cadmium is. And so an electron up here is closer to vacuum than cadmium. Let's take a look at diamond, silicon, and germanium. You can see the band gap shrinking as you go from left to right. Once you get to tin, you don't have a band gap anymore, depending upon the structure of the tin that you're in. Notice there's no conduction band level for diamond. Does anybody want to guess why that is?
Is it because it's above vacuum?
Yeah, it's off scale. Relative to vacuum on this diagram, well, it's 5.5 EV is what they've got listed here. So, that's the valence band is at about minus 5.5. So the conduction band is essentially at the vacuum level. And it turns out that diamond is actually a very good electron emitter. Okay, if you excite diamond with a 5.5 EV photon, the excited electron will actually get emitted. It arcs naturally because the conduction band level is so high. Let's see here. Any other notables? Maybe I'll just point out that the valence band of all these oxides for the most part, although not for this, the ferrites and these tin, bismuth, and iron oxides that are shown here. But all of these titanates and tantalates and transition metal oxides are approximately just the valence band. The valence band level is sort of constant because it's really just an O2 minus sort of an energy. For these sorts of materials, you know, the electronegativity of the partnering element is high enough, and there's sufficient covalency to give rise to some shift in the valence band level. There are scales on here. This is something to be cautious about relative to NHE and relative to SCE. So these are the normal hydrogen electrode and the standard calmel electrode. But this connection between the vacuum level and the electrochemical level is not safe in all cases. Okay, so I wouldn't get too excited about this, but it gives you a sense of you know, where these semiconductors lie relative to the hydrogen and oxygen potentials, for example. So if you wanted to make an oxygen evolving electrode, you know, or a hydrogen evolving electrode, for example, you might pick one of these semiconductors that spans that voltage. All right, so pretty useful table. I think you know, people have them posted in the bulletin boards in the office in my lab. And I think it's available to you on the webpage. And if not, I will go make it available. Okay, so another thing that's wasn't shown on that chart are semi-metals, graphite being a good example. A semi-metal is a much more high conductivity semiconductor, but it's better defined as something that has a zero band gap. So people say a zero band gap semiconductor. Alpha tin is a good example, arsenic, antimony, mercury telluride. The band gap is so small, it's considered a semi-metal. And so the classic one is graphite. You end up with actually two bands of levels here, just like you would see for a semiconductor, but they meet here at this energy level. And these bands are really defined by the pi symmetry orbitals in the graphite. And you can think about these levels as being antibonding pi star-like, and these ones being pi-like. And it's not quite that simple, but you know, that's a way to visualize it. All right. The result, of course, is that these levels right in the middle here are essentially non-bonding like, as we'll see here in a couple of lectures. All right, so let's see here. Define Fermi energy yet? No, there we go. All right, so a metal is something where you know, the empty and the filled levels overlap very well. A different way to say that is that you have a band of orbitals that are partially filled. Okay, and you know, this is one of the ways people talk about this is using the Fermi energy. So the Fermi level here, as labeled in red, this is the energy level where there's a 50% probability of occupation. Okay, sort of a funny definition. When you cool something down to 0 Kelvin, it's the highest occupied energy level. Okay, but when you heat it up, some of the electrons get thermally excited, because in a metal like, you know, sodium or something like that, there are so many different energy levels that are so close to each other that thermal energy is enough to promote an electron from one level to the next. And it turns out there's actually a spread of energy levels that are filled partially right near the Fermi energy. Okay, so it turns out with a metal, if you heat it up, you promote some of those electrons, well, I guess I've gotten a little ahead of myself. The result when you heat something up with a metal actually is sort of a little bit counterintuitive. If you know about semiconductors, the conductivity tends to decrease with increasing temperature for reasons related to scattering. In a semiconductor, the same sort of thing happens. You excite electrons thermally when you heat the material up, and it actually causes an increase in conductivity, as we'll get to in just a few minutes. All right, so the temperature sensitivity of the conductivity is related to this thermal excitation business. The important thing to remember here on this slide is that the Fermi level is defined as the energy level where you have 50% probability of occupation when you partially fill a band in sodium metal. When you partially fill a band, as is diagrammed here, the result is a metallic or a metal. So let's talk a little bit about how bonding impacts the filling of levels with this example of magnesium. So magnesium has a 3s2 electron configuration. And if you take a bunch of magnesium 3s orbitals and you put them together, what you end up with as you change the overlap of the two. So here, this diagram illustrates what happens when you change the magnesium-magnesium bond distance. Those two 3s levels give rise to a strengthening overlap, and the anti-bonding level actually goes up. So the bonding orbital will go down, the anti-bonding orbital goes up, and when you have a molecule, eventually you start pushing things on top of each other, and you get repulsive forces that are driven by overlap of the core orbitals, and that leads this energy to go back up. So there's sort of a preferred distance, the magnesium-magnesium distance, and that's what gives rise to this well here. So when you push two magnesiums together, the bonding and anti-bonding levels split, and in a solid, this same sorts of splitting types tends to happen. And so you might ask for a minute, if you have a 3s2 level that's giving rise to your band, that's where the spread in the band is defined by the anti-bonding versus bonding orbital, would you expect magnesium to be a metal, a semi-metal, or a semiconductor? Okay, it's 3s2. You probably know magnesium is a metal because everybody describes it as a metal, but the highest occupied orbital here is doubly occupied, it's totally filled, okay? And so any combination of those s orbitals is going to give rise to a filled state. So this includes the anti-bonding and bonding level. All right, so these guys both are filled, and any combination in between those guys are filled. So you might sort of wonder whether this thing is actually going to turn out to be a metal. And it turns out that when you do this sort of pushing of the orbitals together, many different orbitals begin to interact. So here's an example showing the 3p, 3s, 2p, 2s, and 1s levels. You push those guys, the atomic orbitals together, and each one of those begins to overlap at different distances. And remember, of course, 3p and 3s are much more extensive. They reach out to the neighboring magnesium sooner than, say, the 1s level. The 1s level is this tiny core orbital. And so at different magnesium-magnesium separations, you see this splitting between the bonding and anti-bonding level sort of kick in. And at the sort of equilibrium distance, there's bonding and anti-bonding going on with 3s and 3p, 2s and 2p. It's not until a little bit closer. And then finally, the 1s level, these guys start to split when they really are on top of each other. So at the equilibrium distance, the 2s and 2p and 1s levels are really just sort of core levels. There's no bonding and anti-bonding going on at all. Now, interestingly, up here in the 3s and 3p part of the spectrum, the bonding and anti-bonding levels for these orbitals actually begin to overlap with each other. Okay, so the bonding combination for 3p is now actually lower than the anti-bonding combination of 3s. Okay, that overlap of dipping below 3p and 3s level is very important to its electronic structure. The 3p level for magnesium atoms are empty, right? So now you've got a bunch of molecular orbitals for all those magnesiums that are empty overlapping with the ones that started out filled. If you write this out as a density of states diagram, you get something that looks a little bit like this. Okay, so at the equilibrium distance, the 1s level is really very, very sharp and narrow. There's no bonding and anti-bonding going on in that level. They don't talk to each other. So all of the 1s orbitals in magnesium metal are at the same energy, and it gives rise to this very narrow collection of levels. The density of states is very, very high at this specific level. Same is true for 2s and 2p, but now when you get up into the 3s and 3p band, you start to see broadening of the energy levels that's caused by this increasing overlap that was diagrammed on the previous slide. Now those molecular orbitals give rise to two peaks, and those two peaks overlap, and they are filled, right, by the 2s electrons, the 3s2 electron pair that came with the atom. And the Fermi energy that's diagrammed, labeled here EF, falls in the middle of this 3s and 3p band that are overlapping. Okay, and that's what makes magnesium a metal rather than a semiconductor or something else, because those two levels overlap. All right, so a very important thing to grasp from all of this is that the strength of the orbital interaction gives rise to what people call bandwidth. Okay, when the orbitals overlap strongly, you get large separations in energy between the filled and the empty states, or the bonding and anti-bonding levels. And this gives you a broad band of orbitals. So in our example of sodium chloride here, zinc sulfide, and zinc telluride, the width of these bands is different on purpose. Okay, and the width of those levels tells you about the orbital overlap and the strength of the bonding. Sodium chloride has very narrow bands because the orbitals don't overlap very well. Zinc orbitals do overlap very well. Tellurium orbitals don't overlap as well. This is a consequence of these being S's and these being P's. Okay, so the width of this band that comes from orbital overlap is a very important property, and it's a consequence of overlap strength. Okay, core orbitals are very sharp. People call those very narrow spreads in energy for a given band a flat band. Okay, we're going to look at a lot of band diagrams, and energy versus momentum diagrams, and you're going to see flat bands. People like to talk about that terminology. That's a statement about the strength of the orbital overlap. All right, I think, I'll finish with this here. Here is a sort of generic diagram for a transition metal. Okay, so I've labeled here 3D transition metals, but this sort of works for the other ones as well. From my class, inorganic chemistry class, we spent a lot of time talking about d orbital interactions with ligands. The 3D is just below the 4s, and then the 4p is above that. You need all those levels to write 18 electron sort of closed shell configurations, but it's really the 3D and the 4s where most of the real bonding happens. In a piece of copper or a piece of iron, those orbitals interact. The 4s and the 3D orbitals interact with each other, and you get bands of the 3D levels and the 4s levels. And depending upon which transition metal you're looking at, the number of electrons changes. But the band structure doesn't really change a whole lot because you're dealing with the same orbitals to begin with. Now, the electronegativities of the elements are all changing and whatnot. The bond lengths are changing, and that's going to make changes. But sort of first glance, simplistically speaking, you can think about the 3D band and the 4S band, and those two bands in a transition metal overlap. And depending upon whether you're looking at copper or iron, the electron, the Fermi level or the Fermi energy in those metals occupies different regions of that band structure. Notice here, the band width of the 4S band is large compared to the width of the 3D band. We spent a lot of time talking about how those 3D orbitals are really important for bonding in transition metal complex because of their energy relative to the ligands. You know, the 4S is higher. But it's also the case that s orbitals are better at making at covalent bonding than d orbitals are. Okay, and so the width of that 4s band is very substantial for that reason. Notice also how the Fermi energy for copper really is, all the action is happening in a region of the band diagram that is defined by the 4s level. Okay, and that has consequences for the conductivity of copper, turns out. All right, so I think I'm going to stop there. Does anybody want to ask a question?
Can I ask a quick question?
Yeah.
I guess you took down the slide, but on the slide before the one you were just on, it looked like
This one.
Yeah, here. So we were talking about like how the 3s and 3p overlap, but it also looks like the 2s and 2p overlap. So why does that not lead to overlapping bands for the 2s and 2p?
So they do overlap if you push the magnesium atoms on top of each other. So the spread in energy and their overlap only occurs when the bond distance is abnormally short. Okay, at the sort of equilibrium distance, there's some parts about this diagram I don't especially like, but the point of this shape here is to illustrate the sort of standard potential well that you think of for a diatomic. That's the equilibrium distance that the diatomic would like to take. Okay, at that distance, there's essentially no overlap between the 2s and 2p levels. They're core levels. If you were to push things together even more, and make and so close that the 2s and the 2p start to interact, then you would get broadening of the 2s and 2p bands.
Okay, so the density of states diagrams are like confined to relevant distances, basically.
Yeah, this is the sort of standard state for the material, which is room temperature, not under pressure. All right. So I will go and make the website available to you with updated dates and whatnot. You do not have a critical review due on Monday, but you do have one due on the 31st. That's the first one that's due. Begin taking a look at the literature, take a look at the examples that are shown there, and start reading. You might even just collect a couple of papers to save for future weeks. As you start finding ones that are meaningful, go in, start figuring out how to keep track of those table of contents. And I will see you on Monday.
Thank you.
All right. Bye, everyone.
Bye. Thank you.